Yep, heat is a form of energy. We're going to talk about that a little bit in this section. We're going to talk about heat, measuring temperature, that kind of stuff. That's the early part of heat. That's section 1. So heat is energy. It's a form of energy or vibration. Whereas temperature is just a measure of how hot or cold something is. Yeah. Now, we could have got more detailed. We could have had a definition which said that temperature was due to the amount of vibration within the molecule, the amount of vibration compared with its mass, etc., that kind of thing. That would have been really useful in proper physics. But no, we're a measure of how hot and cold something is. And those people who have been reading the rest of the slide will realise how annoying I find that. Thermometers. Thermometers are how we measure temperature. This is genuine physics. Thermometry is a genuine branch of physics, and for making a thermometer we need a thermometric property. A thermometric property is something that varies measurably with temperature, i.e. it doesn't just vary with temperature, but we can measure it, and we can measure it in some consistent way. Like, it's not like, nobody has a coat on, therefore it must be colder. Then you go to Newcastle and no one wears a coat at all. No, this is something we can measure, like the expansion of a liquid, the amount of electricity generated between two junctions of different metals, or the resistance varying, or the pressure or volume changing in a gas. They are thermometric properties, varies measurably with temperature. Whereas fixed points, these are places we can be sure where the temperature is. So at sea level, pure water always boils at 0. It's a fixed point. At sea level, it always boils at 100. Did I say boils before melts? Anyway, it melts at 0 and boils at 100. And if you were confused, imagine how I am. And then, of course, you need to divide up the spaces in between, and that's called a scale. Okay, different thermometers. Well, there are some really good ones. So in this one, thermocouple, the first one on the left, that's where you get two different metals, and because of their different electric properties, there's a tiny bit of electricity generated just by touching the two different metals together. This is called junction EMF. It's very difficult to detect. You need a very sensitive galvanometer to do it. But if you do, you find that it varies tremendously with temperature. Now, not in a linear way, as you can see, it's not a straight line graph through the origin, but it does vary in a way that you can easily measure. So you have a sensitive galvanometer and you just touch these two wires together, you're away. Platinum resistance, that's even easier to understand. Later on in the course, you'll see that resistance varies with temperature because of the vibration of the individual atoms. So here, all I'm doing is I'm taking the differences in resistance of the wire and I'm plotting them against the temperature. So the temperature varies with resistance. That's its thermometric property, resistance. Whereas the thermometric property of a thermocouple is called junction EMF. Now, as neither of these are straight lines, we need a thermometer that can calibrate these ones, as well as the liquid in glass thermometer that we're used to, the ones we use in the laboratory. This is a constant volume gas thermometer, CVGT. As you can see from the graph below it, it's a straight line. It's a linear relationship. And we use this one as a standard to calibrate the others too. And it just works with a gas, near ideal gas, a monoatomic gas, and we put that into the liquid and then we readjust the volume until it's back to the original volume. And we measure the pressure that it's put the gas under, because the pressure varies linearly with temperature. Now, different thermometers, therefore, will give you different readings for the same temperature because their thermometric properties are different. Because they have different non-linear thermometric properties, that's why they give you a different reading. This graph is invaluable when answering this question. So, different thermometers. I can't remember what I'm doing here. What's this one about? Oh yeah, they're about calibration. It's calibrated. We did that, didn't we? Okay, I'll move on. Hey, how do we calibrate? Well, this is the way that's down in the book. This is the calibration measure, which is down. You put a known thermometer, which is the mercury one in this case, into glycerol with an unknown uncalibrated thermometer, and you heat the two of them up. Now what happens is that when you get to a known temperature on the mercury, you make a mark on the alcohol, take it out, measure the length, and then you draw a graph of length against temperature, and that's called the calibration curve. The glycerol is there, which is the same what glycerol is used for anything. Glycerol is used because it has a low specific heat capacity, so there's a greater and more rapid spread of heat throughout the material. So it's more likely that the two thermometers will be at the same temperature because of the low specific heat capacity of glycerol, which is interesting to say because we haven't done specific heat capacity yet if you're still on that part of the course. It's the next bit. Okay, there's the calibration curve, so you can take a length and know what the temperature is. I know it's not a curve, it's a straight line, it often is. It's a curve over its full length, so if we went further away from this down to -6 up to 120, it would definitely be a curve. It wouldn't be linear. It looks linear in this range because that's the range we use it in, so it's the one we're most familiar with, and the curve is very gentle anyway. But it is a curve, and that's why it's called a calibration curve. We can also use this more sensible method, fixed points, melting ice and boiling water. Now, of course, as I said before, it has to be pure water at standard temperature and pressure, which means basically sea level. But you can put a point at 0, put a point at 0, and then you put a point at 100, and you divide the space in between into 100 spaces, called Celsius, after a Swedish physicist. If you want Kelvin, after a, well, essentially Irish physicist. He was born in Northern Ireland, Kelvin. Lord Kelvin he was. Interesting man in the extreme. Anyway, Lord Kelvin come up with a possible scale which there wasn't a negative. There's no negatives. It's like teaching in a Montessori school. There's no negatives. Everything's positive. Oh, you've done very well. Oh, you've done that. Oh, that's brilliant. Yeah, but I don't know how you're going to explain it to your parents. That kind of thing. No, what it means is that the lowest possible temperature is 0, which is -273 degrees Celsius. That's the lowest possible temperature in the universe. You can't get colder than that because it's the temperature which all vibration stops. And once vibration stops, you can't get any colder because temperature is vibration. So if you simply add 273 or 273.15 to be really pedantic onto every temperature in Celsius, you get the temperature in Kelvin, and that, it doesn't ever get negative. So heat transfer. This is when you're passing heat from one place to another, and there's 3 methods, and we did this at Junior Cert, so this shouldn't be a shock to you. Conduction, by vibrations along a solid, usually a metal. Radiation, which is travelling by waves, so it's like, electromagnetic waves, like light or radio waves and heat waves. They're all the same sort of thing, just of different lengths. And then convection, which is hot air or fluid rising. Not heat rising, hot air, hot fluids rising. And the way they do it, of course, is when you heat something, it expands. And like a hot air balloon, it floats up. And hot air is the same, it floats up. And we get thermal rising, and that's the main way we transfer heat within a house. So conduction. Heat is put into the bottom left-hand corner, and what happens is gradually the heat spreads via vibration. This one starts vibrating, then that one, then these 3 vibrate, and then that one vibrates, and then in the end they're all vibrating. And it's because they're all bonded together by these nice strong bonds which carry the vibrations from one to the other. So conduction is the transfer of energy through matter, particle to particle, by vibration, and it works, of course, better in solids and even better in metals because metals are closer together and have stronger bonds. Practical conduction, well, that's why the spoon gets hotter than everything else. If you put your hand on the spoon, it'll be hotter than the air around, and the bowl will be hot as well, but not quite as hot. The spoon conducts well. It's also why metals appear cold to the touch, because they're conducting away the heat of our hands, and in this case, the heat of this person's posterior. And water, as a non-solid, is a very poor conductor. Remember this experiment where you heated up the top of the test tube and the ice didn't melt at the bottom? That proves 2 things. One, that water is a poor conductor, and the other thing is that convection actually works only going up. You can't convect down, so convection only works going up. And that is why they put the element of a kettle at the bottom of the kettle so that the heat will rise up. It'll be heating the water up to the top by convection in the same way. And why only idiots and really dickhead architects put radiators up the wall and not very close to the floor where they're going to have the best effect. Okay, another bit of useless information you're supposed to absorb. This is sponge time. Hello, sponges. U value. U value is a measure of how good an insulator something is. A good insulator has a low U value. It allows heat slowly through it. So a good insulator has a low U value. And U value is defined as the rate of heat energy transferred through 1 square metre, where the temperature difference is 1 key. So if there's a 1 temperature difference, i.e. 1 degree Celsius or Kelvin, they're the same thing, between two sides of an object which is 1 metre square, then the amount of energy going through every second is the U value. And of course, if you have an insulator, you want to have that low. You don't want to lose a lot of heat. Whereas if you want something to conduct heat very easily, like the wall of a radiator conduct out into the air, you need something with a very high U value. Convection, fluids rising, circulating, coming down again, you get a convection current. So a current is where it heats up, cools down, comes down again, heats up again, and forms a sort of a rotating current around. This is how most houses are heated, most rooms, from their radiators, which, as some of you might remember, I hate. A radiator is a convector. A convecting current usually is a convector as well. Most heaters in houses work by convection. Why they got called radiators is totally and utterly beyond me. There is a type of heater that glows, that radiates some of its heat. That's very good, but it's not called a radiator because there's already a radiator, and they don't. They convect. Oh yeah, good example, sea breezes. Land gets hot during the day, sea's not quite as hot, so the heat rises above the land and pulls the air from the sea, giving you an onshore breeze, which is why it's always nice and breezy at the seaside, even when it's hot. Right, radiation. The transfer of heat in the form of electromagnetic radiation wave. Now, an electromagnetic wave is a short little wave, tiny, not as small as light, not as long as radio waves. It's in the infrared area, and it's how all the heat gets to us from the sun, because it's the only form of heat that can travel through a vacuum, the absence of any sort of molecules. All the others need some sort of medium to travel in. And when you look at the vacuum flask, you can see that as well. But radiation is the only form of heat that can travel through a vacuum, and it travels by an electromagnetic wave. And it really does it better when it's leaving black bodies. It absorbs it better and radiates it better. So black is a good radiator and absorber of heat. So it transfers the heat very well. Silver is a very poor radiator of heat and a very poor absorber of heat. So you paint a kettle silver so that it won't lose heat when it's heating up, and you paint a radiator black so that it radiates more heat. That thing in the bottom left-hand corner is a radiator. Posh, German, expensive. No jokes about anybody I know. Okay, the solar constant. Back to memory and sponge time. What is the solar constant? It's the amount of solar energy falling on 1 square metre of the atmosphere per second. And it's a rough explanation about why it's hotter at the equator than the poles, because the amount of solar energy is spread over a much smaller area. If you're looking at the poles, they are at such an angle to the sun that 1 square metre of energy coming out of the sun is spread over kilometres and kilometres. Whereas at the equator, 1 square metre is 1 square metre. It's what you see is what you get. So it's an explanation of why it's colder at the poles, but it's also just a simple definition. It's also one of these questions which follows the Bronx rule. If you don't know how to answer this question, you multiply everything together. If you multiply everything together in these questions, you always get the right answer. That's the perfect question as far as I'm concerned. So this is an interesting question I've set. It's about thermometric properties. I've put it all in one page. I hope it makes some sense to you. Read it very carefully. It's a lot easier than it seems.